Okay. So we will continue where we left on sets. Okay. We understood basic idea of sets. We understood the various types of sets in number systems. Okay, natural numbers, whole numbers, real numbers. We also understood the concept of intervals. Okay, so each interval is again a set. I think, and we also looked at very basic types of sets. So today, what we will be doing is we'll be trying to understand certain operations on sets. Okay, so sets is a huge topic. So we are going to look at certain operations on sets. We have been looking at operations on sets. Just say we looked at given a set, you can actually make subsets. Okay, when you are making subsets, you are kind of operating on a set, right? You are taking a set and then you are making various sets. So here, when I say operations, I think we are basically looking at things like union of sets. Okay, you can take a subset, but you can also combine two or more sets. Okay, you can take a common part of two or more sets. That's getting the intersection. Okay, एक difference बोल के है. Okay, so we can take difference of two sets. There's something known as complement. Okay, we will be learning about these. And as we learn about these operations, we'll be taking help of a very important technique called Venn diagrams. Okay, आप Venn diagrams के बारे में कभी सुना? Have you heard about Venn diagrams? Yes? No?
No, sir.
How about you, Om?
No, sir.
No? Okay, so we will be looking at Venn diagrams today. Okay. So Venn diagrams. So what are these Venn diagrams? Now, there's just diagrams on a plane. Okay, you draw them on a piece of paper on screen. The idea is they're going to help us understand the sets. Okay, so you should treat them as a tool. Okay, so they should help us understand sets better. Okay, so that is the idea. So you usually use closed curves, okay, such as rectangles, circles, triangles, and then these closed curves are used to represent sets. So you are learning some kind of representation. So earlier we saw two types of representation of sets, right? We had a set builder form. We had roster form. Okay, in roster form, we listed all the elements in a set. In a set builder form, we have established a property that is applicable for all the elements in a set. Okay, so that it tells us whether a particular object will be part of the set or not. So यहाँ पर we are trying to take the help of diagrams here. Okay, so we are drawing pictures using rectangles, circles, and triangles so that they help us understand sets. The idea is to understand sets. Okay. Now, so rectangle is always used to represent a universal set. Okay, you will always have, what is a universal set? You will always have some set which might contain other sets, right? For example, if I take real numbers. Now, real numbers, we can say contains all rational numbers. Okay, so you can say when it comes to rational numbers, the real numbers set can be taken as the universal set. And then you have natural numbers, whole numbers also as part of real number system. So in that case, you can consider real number system as a universal set. You can do anything. It depends on the context. Suppose if you take integers. Okay, so integers have like even numbers and odd numbers, or even integers and odd integers. You can take the set of integers as the universal set. Okay, so it depends on the context. Now, usually circles are used to represent subsets of the universal set. It's not necessary that we always use circles, but I think the kind of examples we'll be discussing, mostly we will be using circles to represent sets within a universal set, subsets of the universal set. Okay, so now what are the operations on sets that we will learn today? One, union of sets. Okay, union is you're combining two or more sets. Intersection, we are looking at the common part of the sets. Okay, what are the common elements? If you have two or more sets, what are the common elements in those sets? And we will look at difference of two sets. We will see, okay, what this really means, and a complement of a set. Okay, so these are the four operations that we will be interested in today. Okay, so let's start with union. Okay, so understand this clearly. What is this telling? The union of sets A and B. So if you have two sets A and B, this is an operation. Okay, so you need to understand that union is an operation. It is operating on A and B, and it is giving you some kind of output set. Okay, it is going to give you a set which consists of all elements in both the sets. Okay, let's take a very simple example. Okay, so if I take a very simple example, suppose if I have set A of natural numbers, and I'm including only, let's say, 1, 2, 3. And I have another set which includes, let's say, 3, 4, 5. So when you operate on these two, okay, A union B, the symbol used is, I'll show you the symbol. The symbol is this cup. Okay, so when you do A union B, what you're trying to do is you're trying to get all the elements in set A. You're going to get all the elements in set B. But when you do that, you may have some common elements. Okay, if you have a certain common elements, those common elements are taken only once. They're counted only once. So in this case, you see that 3 is common. Okay, because 3 is common, you're going to take it only once. So 1, 2, 3, 4, 5. So that is the union operation. Are we okay here? Okay, so the elements common to sets A and B appear only once. Okay, so this is the idea. Okay, so the operation is written as A union B, and then how do you read it? A union B. Are we okay about this operation? Yes, okay. Now, so how do you write A union B? Because A union B is a set again. Okay, so you need to understand that this is again a set, right? So this is a set. This entire thing is a set. Let me write it this way. So if you look at this entire thing is a set. This itself is a set. So here we are expressing this in set builder form. What are we saying? Okay, so A union B is set of all X such that X belongs to set A or X belongs to set B. Okay, so if you have an element which is in A, it will be part of A union B. If you have an element in B, it will be part of A union B. Now, whenever you look at OR, it always includes both. Okay, OR includes both. So if an element is present in A and B, you're going to include that. But you're going to include that only once. Okay, in the A union B set. Okay, and then these are the Venn diagrams I was talking about. Okay, so these are the Venn diagrams. This is a Venn diagram. So you have this rectangle. Okay, so this rectangle is used to represent a universal set. Okay, so U. And then these two sets, A and B, are part of the universal set. Again, यहाँ तो we have only a diagram. Okay, एक circle है. That circle can mean anything. Okay, so the circle can actually mean anything. For example, I think the common examples that you will see in your textbook is they might give you an example like there are few students in a school, and then some of them play football, some of them play cricket, some of them play both. Okay, I can say that A represents, let's say set A represents students playing football. We can say that it is list of students, sorry, not studying. Okay, so we can say list of students who play football. And then B can be list of students who play cricket. Then A union B. What will A union B be? If a student plays football, he will be part of this A union B. If a student plays cricket, he will be part of it. If he plays both also, he will be part of it. Okay. So this boundary, this entire thing, this represents your A union B. Okay. So when we actually do problems, you will appreciate the importance of these Venn diagrams. They really help us. Questions, guys?
No, sir.
Okay. Okay. So now let us look at the other operation. Now, okay, before looking at the other operation, I think we'll look at properties of unions. So what are some of the properties? Okay, you heard about commutative law, commutative law?
No, sir.
Commutative law in for numbers, addition of numbers you might have seen, 2 plus 3 is equal to 3 plus 2.
Yes, sir, in earlier classes.
Earlier classes. Okay, so that we are using here. I mean, if you first do A union B or B union A, you should get the same set. Okay, so mean to say that the order is not really important. You can place
That
any
means
set.
2 plus 3 will be equal to 3 plus 2, like that.
Yes, 2 plus 3 is equal to 3 plus 2. But not all operations are commutative. Can you give me an example of an operation which is not commutative that you know of?
Like 3 divided by 2 is not equals to 2 divided by 3.
Very good. Okay, so if you do 3 by 2 and then 2 by 3, they're not equal. So not all operations are commutative. Here, for at least sets, it looks very obvious. Okay, so this has to be true because you're anyway taking all the elements. So I think this is a very simple one. And associative is you have 3 sets. Okay, you do first A union B. Whatever set you get, you do union with a third set. Okay, or what you can do is you can first get the union of B union C and then get a union with A. So you will get the same thing. Okay, so this is your associative law. Okay, and the law of identity. Law of identity is if you have a null set. So null set has nothing, right? It has no elements. So when you take A union A, what is that you're going to get? You're going to get A. So it's like in numbers, you're adding 0 to 5. Okay, so if you add 0 to 5, what are you getting? You're getting 5. So 0 is the additive identity, you can say. Identity element under addition. So here, for union, what is the identity element? It is the null set. Do we guys understand this? Okay. Then idempotent law. So that means you're going to get back the same, I mean, A union phi also, you're going to get back the same set. But if you do A union A, what are you going to get? You're going to get A, right? So I think, yeah, these are some properties. Right now, you don't have to worry too much about this. And then law of union. So if you take the universal set, by definition, what are we saying? If I pick a universal set, whatever may be my context, a certain set is inside that union, right? A certain set is inside that union. So universal set union A should give you back U. I think these are okay. These are pretty straightforward.
Yes, sir.
Yes, Peter?
Yeah, sir. It's okay. I
Okay.
understand.
Understood, right? So next is intersection of two sets. Now, what is intersection of two sets? You're
Only
taking,
duplicates are there.
okay, one, I mean, instead of saying duplicates, you can say that you're picking elements which are in both the sets.
Okay.
Okay. So intersection of intersection of A and B gives a set consists of all elements common to both sets. Okay. So this operation is written as A intersection B, and then you read it as A intersection B. Again, if I take that same simple example, if set A is 1, 2, 3, and then set B is 3, 4, 5. Now, when you do this operation, what do you think you will get?
We'll get 3, sir.
You'll get 3. So that's the A intersection B set. Okay, I think this should be easy to understand, right?
Yes. Sir.
Okay, and again, set builder notation, you will write it this way. So A intersection B is again a set. So you're saying set of all X such that X belongs to A and X belongs to B. Okay, so here, if an element is present in both the sets, only then it is going to be part of A intersection B. Now, when we use, let's say, Venn diagrams, circles are used to represent the subsets of universal set. Now, whatever region is overlapping, that would become the intersection part. Okay, so that would become the intersection part. For example, let's say I was talking about students playing cricket and football, right? Suppose A represents number of students playing football, let's say. Let's say there are 25 students. Okay, and then B represents number of students playing cricket. So let's say there are 30 students. Okay, and then let's say total students in a class. Okay, is maybe, I'm just saying 60. Now suppose there are 5 students who play both football and cricket. Okay, so that you place in the overlapping region, intersecting region. So now how many students are playing football only? So 25 are playing football, 5 are playing both football and cricket. So 25 minus 5, so 20 will be playing only football. And similarly, 30 minus 5, only 25 will be playing cricket. So now how many students are playing either football or cricket? You can add 20 plus 5 plus 50. So that means 50 play either football or cricket. Either cricket or football. So that means how many students are not playing any sport? So how many students are not playing any sport?
5.
There are 60 students in a class. If 50 students are playing either cricket or football, 10 students are not playing any. So now this region, the one which is outside, okay, so this region will represent students who are not playing either of the sport. So you can place a number 10 there. Okay, are you okay? So this is how these Venn diagrams are really helpful. थोड़ा time लगेगा to really understand them and use them. But I think when you have only 2 sets, इतना difficult नहीं है. Okay. So when you have 3 sets, yeah, you need a little practice. Okay, properties of intersections. So again, here commutative law holds good. A intersection B is B intersection A. Associative law will also okay. When you have 3 sets, you can first take intersection between A and B, and then do an intersection with C, or you take intersection with B and C. Okay, so you will get the same result. Again, so law of empty set and universal set. A intersection phi is phi. Okay, you understand this now? Okay, now earlier, I think we had one doubt, right? We said your empty set is part of every set, right?
Yes, sir.
Okay, so here, I think this law can help us understand that point clearly, okay? Because I think last time I was giving a room analogy. I said you have a room can be inside a bigger room which is empty.
Yes.
Now, suppose if I consider A intersection B, can I say A intersection B is a subset of A? Can I say that?
Which one is? So A is subset of B. Yes.
No, if I take A intersection B, can I say it is subset of A?
Yes, sir.
Because if you look at this diagram, A intersection B is part of A, right?
Yes, sir.
So that means I can say A intersection B is subset of A. Are we getting this?
Yes, sir.
So whenever I can do that, I'm saying that A intersection B is contained in A, right? I mean, it's just the meaning, right? Now, if I can write A intersection phi is phi, right? If I take A intersection phi is phi, now that means what? Can I say phi is contained in A? Only then I can say this, right? I know it has no elements, but the fact that I'm able to take intersection and then I'm getting phi, it tells me that phi is contained in A. You can argue this with any other set because you're able to take an intersection, right? So if you're taking an intersection, that means A intersection phi is subset of A. Can I say that? Like this. When I say A intersection B is subset of A. So if A intersection phi should be subset of A, right?
Yes, sir.
But A intersection phi is phi itself because there are no elements in phi. That means phi is subset of A. Are you following? A intersection phi is phi. So that means phi is subset of A.
Yes.
So if you take an empty set, this is why we take an empty set to be part of every set. That is a very important point to keep in mind. Okay, so let me go through this logic again. Okay, so when you write A intersection B, what are we saying? If you have A intersection B, that A intersecting B is an overlapping region between A and B. That overlapping region is definitely contained in A, right? It's definitely contained in A. You can also argue that it is contained in B. That is a different matter. But right now, I'm saying it is contained in A. So we can clearly see that that means A intersection B is subset of A. Now, the fact that I'm taking A intersection phi tells me that A intersection phi should also be subset of A. Like this, if A intersection B is subset of A intersection phi should be subset of A. That is what I'm saying. A intersection phi should be subset of A. But what is A intersection phi? Because phi has no elements. The empty set by definition has no elements. That itself is phi. That tells you that your empty set is subset of A. You can also argue the other way around. If you take B intersection phi, you will get phi. So that means B intersection phi, I'll write here, B intersection phi is subset of B. Now B intersection phi is phi, that is subset of B. So if you take the empty set it is subset of every set. Are we okay? Because this is important to understand.
So can you
Yes,
show A intersection 5 in Venn diagram?
That is what, na? When you really show, how can you show in the Venn diagram? It is an empty set, right?
So it is not possible to show in a Venn diagram.
No, well, okay. How do I answer your question? So let's say if I have A, if I'm drawing a circle, the moment I draw a circle, I mean to say that there are certain elements in it, right?
Yeah.
So if I have an empty set, I'm not drawing it, but it's like a dot, right? Now, there is a circle of 0 radius, let's say, because I cannot place any element in that. Now that can be inside A. You understand? That can be inside A.
But it doesn't make intersection, right, sir? Because it is whole in that.
No. But when you say it is going to make intersection, let's say if you think that you're going to say that, okay, there is some phi element that is making intersection. The moment you draw like that, then what are you saying here? You're saying that there are some elements in phi. There are no elements. So ideally what is that you're trying to do is, you're trying to imagine that there is some dot, okay? There is some dot which is representing empty set, let's say. That dot cannot contain any elements. Okay, but you can associate that to be part of any set. You guys understand? It's like 0. Okay, so it's like 5 plus 0 is 5. Okay, so it's the same idea here. Empty set. But it's not exactly the same idea, but here you are treating it as some kind of empty container with no elements in it. And then it is taken to be subset of any set. Okay, it is part of any set. You're not really looking at it, but it is there. Okay, so that is the idea. Oh, okay, so distributive law, I think, let me erase this. Array. You're able to array, 1 second, yes. Let me remove this. Okay, so you're able to look at the distributive law?
Yes, sir.
Distributive law is like you're doing some operation in the bracket. First A intersection B union C you're doing, and that will be A intersection B union A intersection C. Okay, so you are distributing intersection over union. Okay, so that is what you're doing. Distributing intersection over union. Okay, now what do we mean by disjoint sets? Okay, so if you have disjoint, that means there is nothing common. Okay, so if two sets A and B are disjoint, there are no common elements here. So A intersection B is the null set. Okay, so here there is no overlap. Okay, so difference of sets. Now, what do we mean by difference of two sets A and B? So here you are selecting elements which are present in A but not present in B. Okay, so you're only selecting elements which are present in A, but these elements are not present in B. Okay. So the operation is written as A minus B. Again, let's take that simple example. Okay. So if I take the same set 1, 2, 3, and then B as 3, 4, 5. So when you do A minus B, what are you trying to do? You're trying to take elements which are in A, but not in B. Okay, so is 1 present in A but not in B? Yes. So you will take that. Is 2 present in A but not in B? Yes, you will take that. Is 3 present in A but not in B? No. Okay, so it is present in both the sets, so you are not going to take that. Oh, sorry. You're not going to take that. What happened? So let me write it here. A minus B. So this is your A minus B. You're okay?
Yes.
Yeah. Now this is done. Okay, how do you write A minus B? Set of all X that belongs to A but does not belong to B. Now you can clearly see that when you actually have a Venn diagram, this shaded portion is your A minus B. Because here, this region is used to represent elements which are present only in A. They are present in B. Okay. Now, if A is not equal to B, it is important. A minus B is not commutative. Okay, so A minus B is not equal to B minus A. Like your subtraction of numbers also, if you do 5 minus 2 is not 2 minus 5. Okay, the same thing here. A minus B is not B minus A. Again, let's take the same example so that we understand. Okay. So I have A, 1, 2, 3. So these are the numbers. So B, I have 3, 4, 5. So if you look at A minus B, what do you get? You get 1 and 2. If you take B minus A, what do you get? You get 4 and 5, because these are the elements which are present in B but not present in A. So this is different. This is a different set. Are you able to follow this?
Yes.
Okay. Yeah. Okay. Now, what is complement of A? Again, complement. Na, you can. There are two ways of writing complement. ये prime भी चलता है complement, but there is also one more way of writing. You can actually put C at the power. Okay, if you put C in the power, that is also taking complement of a set. Now, complement is basically, I think I'm missing something here. There's 1 second. Okay, so when you actually take complement, you should read it this way, guys. When you take actually complement, A complement, or you can write C in the power. This is basically U minus A. So you are picking all the elements which are present in the universal set, but not present in A. Okay, so this is your A's complement. Now, for example, here, I have a universal set U, and then there is only one single set. Now, what is A's complement? The elements which are outside A in the universal set. Okay, so this, whatever, I think greenish area, okay, is your A complement. I think we are okay. These are the simple operations on sets. So you have union, intersection, difference, and then complement. Guys, before moving ahead, I have noticed one thing. We talked about, let's say, subset and proper subset, right?
What,
Remember?
sir? Can you repeat it?
Subset and proper subset.
Second proper.
See, we said subset. And then we also studied proper subset, right?
Yes, sir.
See, if I suppose if I take A is 1, 2, and then B is 1, 2, can I say A is subset of B?
Yes, sir.
You can say that, right?
Yes.
But what if B is not 1, 2, but B is 1, 2, 3? Then can I say A is subset of B?
Yes, sir.
But what is the difference when I have, let's say A and B are equal? When A and B are equal also, I'm saying subset. When A and B are not equal, when B has an extra element 3, then also I'm calling a subset, okay? But if B has an element which is not present in B, we usually say proper subset. I think we did not really look at carefully on the symbol usage here. Okay, if you have a proper subset, you generally write A, that's sleeping U, and then B. But if you just have a subset, there is a possibility that both the sets are equal sets, right? Like this case, there's a possibility. Okay, so in that case, you should actually write a line between the sleeping U. This is the symbol for just subset. Okay, if you just use this is the symbol for proper subset. Okay, so this generally means that B has few extra elements which are not present in A. Okay, if I'm using that sleeping U and then a line below it, that means B may be equal to A or B may has few extra elements. Both are okay. You're getting?
Yes.
When you are very clear that they are equal sets, maybe you're better of writing a line below. Just a note on those symbols. Are we clear here?
Yes.
Okay, so now do you think you can understand this? If I take A's complement and again take its complement, I should get A again. See, I have a universal set. Okay, so this is my universal set. Inside this set, I have A. So this is A. Now, if I take A's complement, what is that I'm going to get? This region, right?
Yes.
Okay, so this shaded region is my A's complement. But if I take A's complement, then what do I get? I get again A, right? Because I'm not going to take these elements. I'm going to take other elements which are present in U. A is present in U. So you can see that A's complement is going to be A again. Are we okay?
Yes, sir.
Yes. Okay. Okay, so properties of complements. Now again, A union A complement, can I say it is going to have the entire universal set? It's easy to follow.
Yes, sir.
Do you guys understand this?
Yeah, sir.
Okay, and then A intersection A complement, because A complement will not have A, right? By definition, you are taking other elements which are not in A, okay, other elements in the universal set. So obviously A intersection A's complement should be the empty set. Okay, so this is again an important law. Okay, so we will try to understand this using Venn diagrams. So if you have A union ka complement, okay, so if you take complement of A union B, it is A complement intersection B complement. So union kind of becomes intersection, and then intersection becomes union. Okay, so these are called De Morgan's laws. We can easily understand them using Venn diagrams. I'll show you that. Again, so if you take empty set ka complement, empty set has nothing, right?
Yes, sir.
Empty set ka complement, you have everything. That means universal set. So if you take universal sets complement, again you should get nothing. So that is the empty set. Okay, now let's understand this. So here, you guys still remember what this means? N of A?
Power set.
N of A is power set. Harsha, what is N of A? What does N of A represent?
It represents elements of that set A as well. Like that.
Okay, I'll give you a few minutes to. Okay. Okay, so you're able to recall what is N of A?
No, sir.
No?
Superset.
Oh, okay. I will give you some more time.
So finite number from
Hey guys, A is a set, right? It will have some elements. B is a set, will have some elements. So when you write n of A, it is just counting the number of elements in that set.
okay.
That is a symbol is used. That's a symbol used. Number of elements in set A. N of B means number of elements in set B. N of A union B. N of A union B means number of elements in the union set. Okay, now if A intersection B is 5, okay, if A intersection B is 5, what does it mean?
Yes.
That means there are no common elements.
Yes. And
Okay, so if there are no common elements, suppose if I am using the Venn diagram, how do I represent this? This is my universal set. Okay, I'll have a circle to represent A. I'll have a circle to represent B. Now there is nothing common in them, right? Now, can I say A union B will include both, right? So let's take an example here. Suppose in a class, there are 60 students. Okay, so there are 60 students in a class. And 25 like pizza. And then 35 like, let's say, burger. And there is no student who likes both. That means these two are disjoint sets. Okay, there is no student who likes both pizza and burger. Now, in this case, what is happening? 60, can you see, is equal to 25 plus 35? No, because number of elements in A union B should be equal to number of elements in A plus number of elements in B.
yes.
You're okay?
Yes.
Now, what if there are certain common elements? Okay, so if you have common elements, what will happen? How does the Venn diagram look like? So this is your universal set. So there will be an overlap of regions. Okay, so this is your A intersection B. Now in this case, what will happen when you actually try to get how many students are there in the union set A union B? You might add the number of students in A, number of students in A, sorry, number of elements in A, and then you can add number of elements in B. So when you add, what is that you are trying to do? Can I say that you are actually adding elements in the overlapping region twice?
Yes.
So because you are adding twice, what do? You remove them once so that you will get the number of students, sorry. The number of students, number of elements in A union B. You get the idea here.
Yes.
Okay. Okay. Venn diagram समझ में आ रहा है मतलब?
Yes, sir.
It's a representation. It's kind of representation. So sets A and B can mean anything. Okay. So usually problems में क्या होगा? They could mean students playing football or liking pizza, or maybe students taking maths courses or physics courses, things like that. Okay. Okay, this is when you have three sets. So when you have three sets, how do you count the number of elements in A union B union C? Again, let us understand this by drawing the Venn diagram. Okay. So if I draw the Venn diagram here, so this is your universal set. So I'm going to have a set A, I'm going to have a set B, and I'm going to have a set C. Okay, now understand this clearly. If I take the number of elements in A, so if I take number of elements in A, can I say that I'm counting number of elements in A only once, right?
Yes.
Okay, so this region A only once. So what I will do is I'll put a tally mark. Okay, so tally mark to say that I've counted. When I take number of elements in A, I've counted the elements in this region. So similarly, I would have counted these elements, right? All these elements I would have counted once in
Yes.
number of elements in A, right? You guys are getting? Now, when I go to number of elements in B, I will be counting these, but I'm also counting this again, this again, this again. Well, this I've not counted earlier, but okay, I'll be counting this once, but I've already counted, but I'm again counting this. Do you see that?
Yeah.
Now, when I go to, let's say, number of elements in C, what am I doing? I'm going to count this once, but I'm going to again count this region, and this region. But see, if I only stop here, okay, so if I only stop here, that is not going to be correct, right? The number of elements in the union of all these three sets is definitely not number of elements in A plus number of elements in B plus number of elements in C. That is correct only when there is nothing overlapping, right? There are no common elements. Okay, because we have common elements, this is not correct. So that is why what are they trying to do? Because this region, okay, so if you see A intersection B, what is happening? This A intersection B is counted twice, right?
Yes,
So
sir.
you're removing once. So if you remove once, what will happen? Okay, you remove this guy, and then let's say you remove this guy, and then B intersection B you're removing. So if you do that, what will happen? You remove this guy and you remove this guy, and then C intersection A, you remove this guy, you remove this guy. But when you do that, when you actually do these three, you come at middle part, which is representing A intersection B intersection C. So what do? You add that again. Are you guys getting?
Yes, sir.
So this is when you have three sets. So how do you count the number of elements in the union of three sets? Okay, so this is about your theory of operations on. Okay, so here they're saying A and B has two sets. A and B is given. A has 30 elements. B has 55 elements. So if you use what we have just seen, number of elements in A union B will be number of elements in A plus number of elements in B minus number of elements in A intersection B. So you can straight away use this. So there are 75 elements here. There are 30 elements and then 55 elements, and then minus number of elements in A intersection B. So 30 plus 55 is 85.
85.
So number of elements in A intersection B will be 85 minus 75. So that is 10. Very good. Yeah, that is correct. And if you don't want to use this, you can always draw the Venn diagram. Okay. So if you draw the Venn diagram, the rectangle represents the universal set, and then you place those A and B's. Okay, so this is A and this is B. So A has how many elements? A has 30 elements, and B has 55 elements. Now, overall, you have 75 elements. So you don't know how many elements are present in the intersection. That is what you want to find. So you can place X. So if that is X, the remaining region of A will be 30 minus X, right?
Yes.
And the remaining region of B will be 55 minus X.
Mm.
So if you add all those three numbers, okay, so 30 minus X plus 55 minus X is equal to 75. So from here also you'll get X as 10. Okay.
Okay.
Okay, so very nice. So, okay, so try this one. I'll pause for a while. Think about it. So you need to identify the true statements here. Okay, so make a list of the true statements and then we will talk about them. Okay, so now we'll verify which of these statements are true. Who wants to start first? Gautam or sorry,
Me,
Gautam to hai nahi. Om or Harsha?
me, sir.
Okay, so first statement, you tell me whether it is true or false.
Sir, it's false, sir.
Why?
Sir, here x is an element, right, sir? So if you take x as 1 and a as a set of numbers 1 and 2, so x belongs to a here, that is proven. And here a belongs to b. If we take b as 1, 2, 3, 4, then a belongs to b. But in here x
So you are saying, let me correct slowly, go slow. So what you are saying is, you are saying if x is 1,
yeah.
you're taking an example. You think that this is false, so you're proving with an example.
Yes, sir.
Right? That is okay. That is acceptable. So your set A has 1 and 2, and then you are saying B is
B is 1, 2, 3, 4, sir.
B is 1, 2, 3, 4.
Yeah. So like 1, 2 is a set in here, sir. Like it belongs to B.
But here, when they say that A belongs to B, but A is not inside B, right? Look, A belongs to B.
Yeah.
What do they mean is A, the entire set
Yeah, sir,
is an element in B.
Yes, sir. That's sir.
So that means you need to have
At the
so this as a set. So
yes.
in this case, yeah, in this case, your X is not part of B.
Yes,
okay, even though X is like inside a set which is inside another set, like here 1 is present inside a set which is inside B, sorry, but it is not in B. So you're right. Okay, so this is actually a false statement. Okay, so let me clear the board for Om. Om, what do you think about the second one?
I think it's true, sir. Because
Okay, so what? Yeah, why?
for suppose an element 1, 2, 3 is a subset of element 1, 2, 3, 4. That
Okay,
is
so okay, what is your B? You're saying
1, 2, 3, 4, sir.
okay, so B is 1, 2, 3, 4. Okay,
And A is 1, 2, 3, sir.
okay, so A is 1, 2, 3. So A is subset of B. Okay.
Then B belongs to another subset, sir, which is for suppose till 6, and we are including that, sir.
Okay, so 1, 2, 3, 4. So you are including this as a set, and then you have 5
Yeah.
and 6. And then here your A does not really belong to C. So you're showing an example, counter example, saying that it need not be true. So you're assuming, you understand? So this is false.
Yes,
Yeah,
sir.
very good. I think this works. Okay. Okay, so Harsha, your turn. Next.
Sir, I like tried with other examples, but it is showing like different answers for different examples.
Okay. What does your gut feel say? Should this be correct or should
Like
this be
true,
wrong?
sir. I feel it is
True.
true.
Okay, Om, what do you agree with Harsha?
I 1 second, sir. I will just cross check.
Okay, cross. What do you think?
I think no, sir. It would be false, sir, because
Why? Why should it be false? See,
similarly, if we take an example,
see, if I don't take any example, suppose, if I don't take any example, if I say X is an element, X is an element which belongs to A, suppose. If X is an element which belongs to A,
yes,
that means it applies to any element of A, right? I'm talking about when I say X belongs to A and then argue something, I'm really looking at all elements in A, all elements. It is applicable for all elements in A. Now, if A is subset of B, so A is contained in B, right? A is subset of B.
yeah,
A is contained in B. So you can say that X should belong to B also.
yes, sir.
Now can I say that will this apply to all elements in B in that case? Will this X apply to all elements in B?
Sorry.
What do you think?
So can you say it again?
See, this should apply to all elements of B, right? Then X belongs to B. It doesn't mean that it applies to all elements of B, right? The
Yes,
same
yes.
thing when you write, when I say this also, but here I think I am arguing that it is true for all. But here, when it comes to here, X belongs to B, the meaning I think changes a little. You understand? So that is why if you have a diagram, suppose if you have a diagram, A is subset of B. So that means A is definitely contained in B. Can I say that?
Yes, sir.
So if I have B, this is set B, then definitely my A must be present inside B, because that is the meaning of set, right? Maybe A could be a null set. Doesn't matter. If it is a null set, it is basically subset of every set anyway. So this is understood. Now I extend the logic to B is subset of C. That means all elements which are present in B are present in C also. Do you guys understand?
Yes.
So in that case, again, when you move from, let's say, like we did from A to B, when you go from B to C, this X will definitely mean all elements in B. So we can say that, let's say this is C. Now, do you see that A is subset of C in this case?
Yes.
So that means this should be true. Are you guys getting?
Yes.
Okay, I think I'll do one thing. I'll pause a minute, think about it. Okay. Om, explain fourth statement.
I guess it is true, sir.
It is true.
Yeah.
Okay. So how sure are you? Because if I have to prove that the statement is false, I just have to figure out one counter example, right? So here they're saying A is not subset of B, and B is not subset of C, and then A is not subset of C. Now let's say I do a counter example. I'll start by assuming that A is subset of C. Let's say I'll consider A is subset of, say this is A and this is C. A is subset of C. A is contained in C. Now, if you take A is not subset of B, suppose. If A is not subset of B, I can, what is that I need to do? I just have to have some elements which are there in A but not in B. Simple, right? I have to have some elements in maybe all elements in A which are not present in B. So if I have B outside, then what will happen? Is A subset of B? Then this is true. A is not subset of B. This is also true. B is not subset of C. But is this true in this case?
No, sir.
Are you getting what I'm saying? So that this is actually a false statement. No?
Yes, sir.
I'm giving you an example. I'm giving a counter example that this is not true.
But we can also say it's true, right?
We can
sir?
also say
It's true. If we have C at another.
no. If it is false for even for one example, then it is not a true statement. It is false. See, I think proving that a statement is true in all cases is difficult. But if it is false, you just have to show one example.
Sir, how can
I'm
we
showing-
say A is a
I'm
subset of C?
I'm showing you, na beta. See, what this statement is saying is, if the first two statements are true, then we are saying A is not subset of C. That is what we are saying, right? But I'm
Yes.
saying the first two statements are true. A is not subset of B. They have nothing in common. Okay. B is also not subset of C. They have nothing in common. But am I not showing you that A is subset of C? Right. See, if this statement has to be true, then what will happen? If this is true, then this must be true. Only then this statement is true. Or alternatively, if this is false, then I can't say anything. Then I can't say anything. Okay, we will study about this if then later in detail.
Okay, sir.
You understand? So I think this should be a false statement. Okay. Okay, Harsha, you try to explain this fifth one. What do you think about the fifth statement?
Sir, it's false.
Okay, why?
So you're saying like if we take X as an like 3, then we can take the A set as a 1, 2, 3, sir.
Okay, so X is what you're saying?
3.
X is 3, okay. Then
A set would be 1, 2, 3, sir.
1, 2, 3, okay.
Then here we are saying A is not a subset, so we can say B is 4, 5, sir.
Okay, B is 4, 5, okay.
Then if we check this, then X doesn't belong to B, sir, so it's false.
Okay, X does not belong. So you have a counter example that this statement is not true. So this is false. Okay, very good. Okay, Om, how about the sixth statement?
Sir, I guess that is also false.
False. Okay. So if A is subset of B, can I say A is contained in B?
Yes, sir.
And if X does not belong to B, what does it mean? It is not in B. So can it be in A?
No, sir, it cannot be.
So that means it is true.
Yes,
You guys understand?
yes, sir.
See, A is actually contained in B. A is subset of B. Now, when you say that some element does not belong to B, that means it is outside B, right? So if it is outside B, it is also outside A. Om, do you understand? So this must be true. So overall, how many statements are true? There are 2 statements that are true. Are you guys getting this?
Yes, sir.
Okay. So, okay, so let's move on to the next problem. I'll give you some time here. Okay, now, okay, so I'll pause for 1 or 2 minutes here. Think about it, whether this is true or not. and then try to get a justification using a Venn diagram. Okay, so take the help of Venn diagrams. Okay. So let's discuss this. Okay. Now suppose let me draw this. So if I take this universal set, and inside this I have A, and then let's say I have B. Okay, so this is A, and then this is B. Now you see that A union B. Okay, so this is your A union B, right?
Yes.
This entire thing is A union B. Now I'm saying this is equal to A union C. Suppose if I get a set which is equal to C, then it is possible that B equal to C. But what if I just want A union B is equal to A union C? What if I get my C containing some extra elements which are there in A but not in B? Can I use that as my C? Do you see that?
Yes.
See what I'm saying? This is my A, this is my B, but my C is this extra thing. In that case, A union B is equal to A union C, right? But is B equal to C in that case?
No, sir, it isn't.
So I'm showing you an example where it need not be. So that means this is not true. Okay, so this is no. The answer is no. Are you guys getting this?
Sir, it can be true also.
See, true also, then the statement will not become true. Even if there is one specific example where it is false, you take the statement to be false. When it is true, it should be true for all cases, all situations. In general, it should be true. Are you getting this?
Yes, sir.
Okay, so now let us see if you can justify this. Is it true that if A intersection B is equal to A intersection C, then B equal to C? Okay, again, I don't know why I have this question mark. Ignore that question mark. Okay, so justify your answer. Again, I'll pause for a minute. Okay, so try this. Very good. I think this again would be false, right? So
Yes.
can you show me the same logic here again? Let's say if you take the universal set and again take A and then B. Now what we can do here is A intersection B is correct. So I can always take a set which is having that A intersection B, and then this can be just C, right?
Yes, sir.
This can be C. Okay, so this can be C. So then A intersection B is equal to A intersection C, but you clearly see that B is not equal to C. So this is no. Okay. So now what I will do is I need this diagram and then this diagram. Let me copy these two diagrams. Where is the diagram? Let me copy this. Let me put it here. Why is it not coming? Paste. Okay. Let me copy these two together. So now you should. Okay. Now can you see this statement now? Can you see this statement? And then think about these two examples. If A union B is equal to A union C, and then A intersection B is equal to A intersection B, then I can say B is equal to C.
Yes, sir.
Because if I take this case, okay, so this is the case where your A union B is equal to B union C. So here C has few extra elements compared to B. Otherwise, C is almost B. Okay, otherwise C is almost B, but C has few extra elements which are part of A but not in B. So you want to eliminate this scenario, right? You want to eliminate this scenario if B and C should be same. But when you want to eliminate this, what are you trying to eliminate? You're also trying to eliminate these kind of elements, right?
Yes.
You're getting the idea.
Yeah.
So when A union B is equal to A union C and A intersection B is equal to A intersection C, then B should be equal to C. Okay, you're getting, I think I'll pause here for a minute. This is important. So think about it. Let me know if you have any questions. See, the idea here is, understand this. Here, all we are saying is, if A union B is equal to B union C, but by creating some region of C which contains elements in A but not in B, what are you trying to do? You are kind of making the second statement false, right? In this case, your A intersection B is this, but your A intersection C is this. Do you see that?
Yes.
You want to make that true also. So that means you want to remove this. Getting?
Yes.
But if you say that only the second statement is true, A intersection B is equal to A intersection C, but if there is a gap between B and C, then what will happen? This will be false. So you don't want to have this gap also. Okay, so if both the statements are true, then you can say definitely B is equal to C. Are you okay? Om, are you getting this?
Yes.
Okay, so try this. I'll give you 2 minutes to work on this. Okay, so I think Om is correct. We'll discuss this. See, again, I can have a universal set. This universal set tells us the number of people in the apartment block. So I can have a circle which represents number of people who watch Netflix, and have an overlapping circle to represent people who watch Prime. So they're saying 22 watch Netflix or Prime, right? So if 22 watch Netflix or Prime, that means this region, right? So this region represents that number, this entire thing. Now 11 watch Netflix. So 11 watch Netflix, this is the region that represents Netflix. 6 watch both Netflix and Prime. So now can I start from there? I can say that, okay, 6 watch both Netflix and Prime. So I'll put 6 number there. How many watch Netflix? 11 watch Netflix, right? So only Netflix, how many will watch? 11 minus 6. So that will be 5. Right. So now this is how much? 5 plus 6 is 11. Now the remaining should be what? 22 minus 11. So that would be 17. You guys understand? 22 minus 11 is how much? 11.
Sir. Yes, sir.
Sorry, what am I saying? 22 minus 11 is 11 only, not 17. Okay. I think I got biased with the answer. Okay. So this is 11. But what is the question? This 11 represents people who watch only Prime.
Yes, sir. 17.
Okay. So there are people who watch Prime and Netflix 6. So overall, kitna ho gaya? 17. So 17 should be the answer. Okay.
Yes.
Okay. So I think we'll do one thing better. We can stop here and then we'll continue on Friday.
Okay.
Okay. Okay. So what I will do is Friday, shall I give you homework?
Yes, sir.
I'll do one thing. I will post this PDF. Okay, I'll post this PDF in Google Drive and then share the link with you guys. So try to complete the other problems. We will discuss them on Friday. Is it okay?
Yes.
Huh? Yeah.